All right, everyone up, everyone up. Okay, half the people are up thus far. Okay, spend a minute, do some stretches, jumping jacks, whatever you need to do to wake up. All right, if you guys want to get seated. Okay, so who's excited about CS70 review? Okay. So I'm going to be going over propositional logic, proofs, and induction today. So we're going to start off with that. So just some brief review. If you remember, a proposition is just something that's true or false. Something like our class has 2 midterms, which is true in this case, or something like 3 is even, which is false. And just to remind you guys, we have and, where if we have 2 propositions, in order for it to be true, both the propositions must be true. We have or, where at least one of them must be true. We have a negation, so if a proposition is false, then the negation of it is true. And we have implies. So for example, if P implies Q, like up there, this is only false when P is true and Q is false. So implies just tells us that if P is true, Q also has to be true. So I know most of this is review for you guys, so we're just going to jump into a practice problem from Sahai's fall 2014 midterm. So if you guys want to get out some paper or just do this in your head. So the problem is, this is a truth table for XOR. So express it using ands, ors, and nots. And then you want to see if A XOR B implies A or B, and if A or B implies A XOR B. So find a partner, get a piece of paper out, and take a minute or so to work on this. And if anyone has any questions, just raise your hand. Does anyone have any questions so far? You guys don't have any questions? You're all good? No questions? Okay, does anyone need another minute? Raise your hand if you need one more minute. Okay, one more minute. And it might help to think about B or C intuitively rather than writing out a truth table. Okay. Is everyone done? Okay, let's go on towards the solution. So, okay, you can express it in any of these three forms. So either A is true and B is false, or A is false and B is true. Either they're both, what's a good way of explaining this? Either it's, or you can have A or B, but they can't both be true. So basically all three of them are explaining the same thing. The most intuitive way to think about it, in my opinion, is just A. So for B, does A XOR B imply A or B? So A XOR B, so just not even looking at these equations, right? Let's just think about this intuitively. A XOR B is only true if A is true or B is true, right? And A or B is true if one of them is true. So A XOR B is true if A XOR B is true if A is true and B is false, or if B is true and A is false. So at least one of them has to be true, so A or B should be true. And for C, does A or B imply A XOR B? Does anyone want to try and explain this to me intuitively? Yeah.
It means when A or B is true, that A XOR B is also true.
Right. So, okay, why is this not the case? Because A or B is true when both of them are true as well, right? A can be true and B can be true. But then A XOR B would be false in that case, because only one of them could be true. So A or B doesn't necessarily imply A XOR B. And if you don't believe that, you can also draw out the truth tables. So that's a good exercise to do at home. Does anyone have any questions about this? I know there's a lot of truths, ors, and ands I just said there. Yeah.
Can you explain intuitively why AX or B implies A or B?
Okay, so it might help to write this out. There's no chalk. That's okay. Okay, so A XOR B is right. A XOR B is only true if A is true and B is false. So if this is A, this is B, or A is false and B is true, right? And in both of these cases, you're trying to see if this implies A or B, right? And in both of these cases, this is true, right? So you're trying to see whenever this side is true, whether this side is true, right? So you try, okay, if A is true and B is false here, well, this is true. And if A is false and B is true, then it's still true. So the idea being XOR is a kind of a tighter bound, or tighter constraint. Any other questions? Okay. So just some quick review on quantifiers. If you remember, the for all symbol is used to make a claim about everything in a set, and the exist symbol is just used to make a claim at least about one object in a set. So we're going to do some quick practice. I just pulled these right off of discussion, so if you guys want to try and convert these into a statement with quantifiers instead, just take a minute or two. We did this in discussion, so it's review, but I think it's good to do for practice. So. Does anyone have any questions about it, or wants me to come and check their work, etc.? Okay, so if you guys finished one, that's the answer for one. You can check your work, and we'll go over both in a second. And number 2. Okay, so I think these ones are pretty straightforward. The first one is just saying for any integer, if it's not 0, then its value squared is greater than 0. So for all n inside z, so for any integer, if n is not equal to 0, n squared is greater than 0. And for the second one, we just say for any x and y we choose inside the integers, there's no solution to x squared minus, let's see. For any integer we choose, any two integers we choose in z, x squared minus y squared won't be equal to 10. So both pretty, yeah.
Is there any direct way of saying there exists no integer? For every negating.
There's also another symbol you can use. It's like the e and then with a slash. Yeah, but I think this way is easier to state. So you could say like there does not exist x, y such that this is equal. Yeah. Because the idea in 1 was that as long as n is not equal to 0, then n squared is greater than 0. But 2 is making a claim about every integer. So there's not something that has to. There's no constraint, so to speak. Yeah. So that's another way of stating it. So if you say for all n inside the integers except for 0, you wouldn't have to put the implication. Any other questions about this? Okay, so I know we went over that quick, but we're going to move on to proof techniques. So there was a couple proof techniques we went over during class. There's direct proof, where if like P implies Q, you assume P is true, and then you just try and prove Q. And then we have proof by contraposition, which we say if P implies Q, we try and prove that not Q implies not P. So if you draw out the truth tables, you'll see that these two, P implies Q and not Q implies not P, are congruent. And then we have proof by contradiction, where you assume that the claim you're trying to make is false, and you show that this leads to a contradiction. And then you also have proof by cases. So you might have a problem that tells you prove a certain condition about all integers, and you can break up these integers into evens and odds, and that'll help you prove the statement. So we'll just jump right into some problems. The first problem's pretty straightforward, and then they get progressively more difficult. So the first problem should not be that hard. You should try to identify what proof technique this is, and then try and prove it. Surprised. Oh, no, I forgot. I'll give you credit during the presentation. Yeah, does anyone have any questions about this? Does anyone know what proof technique we're using for this? Does anyone want to suggest one? Right, direct proof. So maybe another 15, 20 seconds. Okay, so let's go over the solution. Again, we just pick two numbers, say that they're both odd, multiply them together, so we have m times n. And as you multiply them together, you should see you're able to factor out a 2, and you'll have a 1 remaining as a 1 remaining on the outside. And by the definition of a odd number, this is also odd. Yeah.
Is it possible to do something simpler, just like a concrete example? I mean, that's proof that it's not.
Well, in this case, the statement is true. Yeah. Does anyone have any other questions about how we prove this? Okay. If no one has any questions, let's go to practice question number 2. So this one's not that much more difficult. So you should try and figure out... Okay, actually I'm going to give away the hint. Okay, prove this with contraposition, because you could do it either way. And try not to just brute force n. Try to use a theorem we learned. And remember to raise your hand if you have any questions. Okay, does anyone know what theorem we use for this? Okay. So this one, again, should be pretty straightforward. You just say if n is a perfect square, it can be written as k squared. And then by Fermat's little theorem, you know that this is equal to 1 mod 3. Therefore, n mod 3 is not equal to 2. So we just prove the contraposition, and therefore we prove the original statement. So this is an easier problem, but it's meant to show the point of how we do how we use contraposition. So does anyone have any questions about this? Okay, this one was pretty straightforward. So the next one, I think, was in the notes, but we're going to go over it anyway. So we want you to prove that root 2 is irrational. And I want you to try and figure out, so this one's definitely a harder problem. So I want you to figure out what proof technique we're going to use here and how we do it. So maybe identifying the proof technique is more important in this case than actually how you solve the problem. Does anyone know what proof technique we're going to use for this? Contradiction. who feels like they need another minute for this? This is a bit tricky, so if you don't know how to do it, it might take a while. This is a harder one. If you have questions, raise your hand so we can come around and help. Does anyone have any questions? Is anyone stuck? Is anyone not stuck? Just remember to raise your hand if you have questions. Okay, I think we're just going to go over this because this is a bit tricky. So we said if we assume for contradiction that, so we're going to do a proof by contradiction. So we assume that there is some a and b such that a over b is equal to root 2. So we assume that it is rational. Right, we're trying to prove that it's irrational, but since we're doing a proof by contradiction, we're going to assume, for the sake of contradiction, that it is rational, and we're going to assume that a and b are simplified. So the proof here is a little bit slick. So if you don't get it first time around, make sure to ask questions. So we can bring the b over and square both sides. So we have a squared is equal to 2b squared. So that implies that a is even, and that also implies that b is odd, because if b is even, then a over b is not in its lowest form. So since a is even and a over b can't be simplified any further, b must be odd. Because if b was even, then we could divide out a 2 on both the top and the bottom. And because a is even, a squared is a multiple of 4. So we can divide by the 2. So we have a squared is a multiple of 4, right? So let's see. So we have a squared is a multiple of 4. So we can say it's the same as something like 4k squared. And we have this is equal to 2b squared. So we can simplify this and we'd get b squared is equal to 2k squared. So now b also has to be even. So b can't be both odd and even. So there's a contradiction. Again, the proof for this is kind of slick, so. Okay, does anyone have any questions about the first thing we said? Okay, does anyone have any questions here? Yeah. Yeah. So we have a squared is equal to 2b squared, right? So in that, because a squared is equal to 2b squared, a must be even. Right? If a is odd, then something odd squared is odd, right? And that can't be equal to an even number. So on the right-hand side, 2b squared is an even number, right? Let's say a was odd. Then a squared would still be odd, but it's equal to some even number. Does that kind of clarify it? Yeah.
So how do you know B is odd?
So the reason we say B is odd is because we initially assumed that A over B is in its lowest form. So it can't be simplified any further. And if B was even, then both A and B are even numbers, right? And you can always simplify an even number over another even number. Does anyone have any other questions about this? Yeah.
How do we know it's a multiple of 4?
Okay, that's a theorem you can prove. But basically, if A is even, okay, so we know A is even, right? So then A squared would be 4 times whatever, right? If A is even, A is equal to 2 times some number. So then A squared is equal to 4 times some number squared. Again, this is pretty tricky. Any questions before we move on? No one has any questions. Okay. We're going to move on to induction. And if you guys remember the three basic things that we do when we're trying to prove something with induction. First, we have our base case. Then we have our inductive hypothesis, where we assume that it's true up to some k. And then we have our inductive step, where we're trying to show that the k plus 1th case is true. And usually the most natural thing to do is try and find the kth case when you're trying to prove the k plus 1 case. So maybe an example would be helpful here. So, okay, this was off a past midterm, summer of 2014. So if you guys want to try this one out. And not very many people have raised their hands. So just make sure, if you have a question, make sure to ask. You don't want to have a question about this during the final. So. There's one more problem after this, so yeah. Is there anything I should be changing or doing or? Who needs another minute for this? Okay. Just in case not everyone remembers. Does anyone have questions before we go over the solution? Okay. So, what's our base case here? 1, right. So, okay. You have f of 1 and f of 1 and f of 2. So the GCD of those is obviously 1. You have your inductive hypothesis, so you assume it's true for up till n, and then the inductive step, we just break this up into f of n and f of n plus f of n minus 1, and if you guys remember the hint from the last slide, where GCD of a and GCD of a plus b is equal to GCD of ab, we basically use that here, and simplify that to f of n and f of n, the GCD kind of went on the other side, but okay. We do GCD of f of n and f of n minus 1. And from our inductive hypothesis, we know that's equal to 1. Does anyone have any questions about this proof? Yeah. Oh, no, it was. Yeah. The hint that I gave was on the original final. Does anyone else have any questions? So you'd have build-up error if you were trying to work backwards, right? So let's say I took the case where, let's say I took my inductive hypothesis, right? And I was trying to push that forward to become my, like, the idea is you start at your k plus 1 and you work downwards. You don't start at k and work upwards is the idea. So if that makes sense. So you take your k plus 1th case and you try and break it down into smaller cases rather than take your kth case and try and build it up. Yeah.
What is n?
So that's just the nth Fibonacci number. Yeah. Yeah.
So do you have to do this proof by induction since you guys built up in the first case, or can you do it in this?
I'm sure other ways exist, but induction is one that I would say one of the easier ways to prove this. Any last questions? Okay. Oh yeah, sorry.
So why is it fn plus fn minus 1? Why does that break?
Right, so do you remember how the Fibonacci numbers, we get the f of n plus 1 from taking the previous two and adding them up? Yeah. Okay, no more questions? So we're going to have one more practice problem, but if we just recall the definition of strong induction, we're basically doing the same thing as regular induction, but we're making a stronger claim, which is it's true for up to k instead of it's true for exactly k. So we're going to be using that. Credit to Hugh for writing some of these slides. And then we have recursion. So there's no practice problems on this, but just to let you guys know, the induction and recursion basically go hand in hand. And you can use induction to basically prove the correctness of your program, but you can also, sometimes it's helpful and actually helps you discover how you should write the program. So, just a quick debrief on that. So, okay, this is our last problem. This one's a bit harder. So, you're given some sequence, you have the first three terms, and you're trying to prove that the addition of the last three terms is always less than 2 to the n. So for this one, if you don't have a partner, find a partner and try and do this one together. No one is finding a partner. Do you guys want to work together, maybe? Come on.
Okay. Yeah, you just tried out the first couple.
And raise your hand if you have any questions. Sorry, let me come around. Yeah.
How did you get from fn plus 1 to fn plus fn minus 1?
So, okay, if you remember, that we're working with Fibonacci numbers, right? Okay. So the n plus first Fibonacci number is just the addition of the previous two.
Okay.
Yeah.
Okay, and then on this one, we know that b can't be like 2. Is it because like then a would be square root of 8?
Or like, okay, so in this case, so don't think about like what b and a can be in terms of numbers, right?
Okay.
So we're just trying to prove with contradiction. So we just say, okay, assume any a or b exists, right?
Okay.
Or some a and b exists that makes this equal to square root of 2, right? So when we multiply this here, so do you get how we get that a is even? So from this equation, do you get how we get how a is even?
No.
Okay, so if a is odd, right? What is an odd number squared?
Even.
Not even, right? So 7 squared is like 49, right?
Oh yeah.
So an odd number squared is always odd.
Oh yeah.
So since an odd number squared is always odd, we have odd on this side, we have even on this side. Right? So that means that's a contradiction. So A has to be even.
Even. Okay.
So then if A is even, then B has to be odd. Because if B was even as well, then this wouldn't be in its lowest form.
Okay.
Does that make sense? If both were even, we could divide a 2 out. We could simplify by a 2, right?
Yeah.
So then we know that B is odd. And then since A is even, A can be written as a multiple of 4. So we can have A is equal to like 4k. A squared is equal to 4k squared. So that might be helpful to write. So you say like A squared is equal to 4k squared.
So like A is 4k squared.
A squared is, right? Because A is even. So if A is equal to 2k, then A squared is equal to 4k squared. So then we say 4k squared is now equal to 2b squared. And then now we find that B is even.
Okay. Okay. Thank you.
Okay, so who wants another minute on this? Okay, 1 more minute. We're running a bit short on time, so. Okay, let's go over the solution. So in this case, our base case is just when A is equal to 4, right? So we just add up the first 3 numbers, 1, 2, and 3, and we get 6, which is less than 16. So it seems like the base case holds. So for our inductive hypothesis, we do a strong induction. So we assume AI is less than 2 to the I for all I from 5 to k minus 1. And for our inductive step, okay, so this is a bit of algebra involved, so we can go over I can answer questions about the algebra after, but basically what we do is we just substitute in, so we know that A of k minus 1 is less than 2 to the k minus 1, we know A of k minus 2 is less than 2 to the k minus 2, and we know if A of k minus 3 is less than 2 to the k minus 3. So we basically just use our inductive hypothesis, and we substitute that in, but we know it's less than. And then we just factor out the 2's, so we get a 2 to the k minus 3 term. And then when we do that, we get that is equal to 7 times 2 to the k minus 3, which is less than 8 times 2 to the k minus 3, which is less than 2 to the k. So we're basically working, yeah. It doesn't matter. It can go to k. Yeah, it's the same thing. Yeah. Well, in here we use strong induction because, so if we were using regular induction, right, we would only know the bound we would be only using the bound for A of k minus 1. But we want to also use the bound for A of k minus 2 and A of k minus 3. So like, let's say A of k minus 2, right? We're using the 2 to the k minus 2. And do you see how we're not just using the previous case? We're using cases before that as well. So that's where the strong induction comes in. This one's a bit tricky. Does anyone have any questions? Oh, so how do we get the 2 squared plus 2 plus 1? We just factor out 2's until all the terms are 2 to the k minus 3. Okay, so strong induction comes into play when we're trying to find the bound, right? So it's the first line of the inductive step where you'd see the strong induction. Because in regular induction, we would only be doing something like A of k, like the fact is that we're using a bound from cases that aren't previous to A of k. So we're using A of k minus 2 and A of k minus 3, right? Those aren't immediately before A of k. So strong induction comes into play because we're using a case which isn't right before A of k. So, yeah. Yes. So we know A of 1, A of 2, and A of 3. So you can also yeah. Right. So where do we get that inequality from? That's from the hypothesis. Any last questions before I pass the mic? Okay. Okay. Sorry. Yeah. Okay. Hi everyone. I'll be going over countability and bijections and computability. So let's see. So first, injections, surjections, and bijections. So if you look at the diagram here, f is a function from x to y. F is an injection because for every element in y, there's at most one element in x that maps to y. G is from y to z, is a function from y to z. G is a surjection because every element in z has at least one element in y mapping to it. So as a quick exercise, so come up with functions with domains and ranges that are both over the rails, and they are both that satisfies the properties here. So any questions so far about this question? Okay, so the question is, what's the difference between a bijection and injection? Well, a bijection is an injection and a surjection. So a bijection is both injective and surjective. So a function that is injective and not surjective is not a bijection. Does that answer your question? Okay, one more minute. Okay, so
here are some answers. There are many answers. There are uncountably, infinitely many answers. So so which brings us to the next topic. Okay, you can take a look at these later, but yeah. So countability. So countability. What's countability? So if you have two sets A and B, a bijection from set A to set B means that their sizes are the same. In fact, that's how we define the size of a set. If there's a bijection between two sets, then they have the same size. Yeah, and if there's an injection from A to B, that means A is smaller than B. Because if you look at diagram here, there's an injection from X to Y, and Y is at least the size of X. Okay, so then if A is smaller than B and A is bigger than B, then A is equal to B. So this might be obvious, but it's not really obvious for infinite sets. So here are some examples of countably infinite sets and examples of uncountably infinite sets, and here are some exercises. Yeah. So any questions for exercises? Any questions about these questions? Okay, a Bernoulli random variable is like a coin flip with probability P of getting hits. P is between 0 and 1. Any other questions?
What is a function from 0 to 1 naturally?
Okay, the question is for number 3. So what's a function from 0 to 1 to naturals? It's a function with domain. The domain of the function can be two numbers, 0 or 1. The range of the function is all natural numbers. So if you've been to a midterm 2 review session, question 3 and 4 are the same. Okay, so let's go through the answer for the first one. So, who thinks that Bernoulli random variables are is finite? Who thinks for number 1 it's finite? The set is finite. Okay, who thinks for number 1 set is infinite, countably infinite? Who thinks that it's uncountably infinite? Okay, so I think the majority is uncountably infinite. Yeah. So Bernoulli random variable consists of parameter p, which range over 0 to 1, and it ranges over the reals from 0 to 1. So since the reals from 0 to 1 are uncountable, then therefore this set is uncountable. Okay, what about question 2? Who thinks it's finite? Who thinks it's countably infinite? Okay. Who thinks it's uncountably infinite? Alright, yeah, the answer is that number 2 is countably infinite. So it's countably infinite because this is essentially taking all pairs of, let's say, all pairs of strings, which is since each one of them are countable, that means the set of all pairs is also countable. Okay, so question 3. All functions from 0, 1 to naturals. So I don't think so who thinks it's countably infinite? Okay. Who thinks it's uncountably infinite? Some people. Okay. So let's take a look. So how do you write down such a function? So we write down such a function by Alright, so all functions from 0, 1 to naturals. So the function takes in 0, 1 and it outputs a natural number. So so you can say that this one such function is f0 equals to some number a, and f1 equals to some number b. So you can represent this function as this pair a, b, where a and b are natural numbers. Okay, so you can see that this is the same as just pairs of natural numbers. Therefore, it's countable. Okay, so the last one, who thinks it's countable? Who thinks it's uncountable? Okay, so let's take a look. All functions from naturals to 0, 1. Okay, so how do you write down one such function? You can write down one such function by taking a look at so for every single natural number, starting from 0, 1, 2, 3, 4, all the way, and one function can be encoded as so for each number, it can be either 0 or 1. So arbitrarily 0 or 1. So you can see that each function is an infinite bit string. Each function can be encoded as an infinite length bit string. So therefore, the set of all such functions is the set of all such infinite length bit strings, which is uncountable. Yeah, question? Yeah, so each function can be represented as an infinite length bit string because you want so for each natural number you want to store a function value, its function value, the value of that function on. Yes, each function is stored as an infinite length bit string. Functions could be defined in so functions can be defined as like a mapping between input and output, right? So it could be like the set of all functions could be it doesn't say anything about whether it has to be countable or not. Is that the question? Okay. Yeah. So that's countability. So finally, we come to the halting problem and computability. Okay. So I can give you the proof of the halting problem. You can take a look at it here. So, but actually, the questions that I'm going to give you doesn't really require you understanding or the proof of the halting problem. So, for these two questions, try to somehow use the halting problem. Use the fact that if you can, use the fact that if you can construct a program that solves the halting problem, so it's not this program is like uncomputable. So the first one, yeah. So you can take a look at these questions. Okay. Okay, so who thinks the first one, who thinks it's possible for the first one? Does exist a program that does that? Who thinks it's possible? Raise your hand if you think it's possible. Okay, who thinks it's not possible? Okay, so who doesn't want to raise your hand? Why are you raising your hand if you don't want to raise your hand? Okay, okay. Okay, in fact, this is like the essence of like the proof of the halting problem. Okay, so all right, so let's take a look at it. So the answer is that it's not possible to write such a program. It turns out that if you can write a program, you can write this program, then you can solve the halting problem. So we can take a look here. So we define this program HALT, which will solve the halting problem if you could find this if you could define the program R, which is what we want. So you first define another helper function which runs the program, and if it halts, it returns CS empty. So it outputs CS empty if and only if it halts, and then you run this R, this program that you're wondering whether it exists on A, which is what you defined. Okay, so here, so if R exists, then you can solve the halting problem. So the second question is describe a real number that's not computable. So you could encode the result of so you can write down a list of all the programs, all possible programs, because since they're like there's a bijection from all programs to natural numbers, you can write them down in a list, and for every program, right next to the program, 1 or 0. So it's kind of the same as what we did here. So if you have a list of program P1, P2, P3, and so on. So write 1 if it halts, write 0 if it doesn't halt. Right, 1 if it halts, right, 0 if it doesn't halt. So, and then you put a 0 point in the beginning. So you get a real number. You get a real number that is not computable, because if you could compute this real number, you can solve the halting problem. So there exist numbers that are not computable. So I'll leave you to think about that. So I think that's the end of my my review. So I'll hand it to the next person. And yeah.
Sorry. Okay, so I'll be covering stable marriage and graphs. So I'll start out with stable marriage. And for stable marriage, let's start with a joke. So, how do you fix a broken tuba? With the tuba glue. Okay. So for stable marriage, the problem we're trying to solve is you have some men who rank women and women who rank men, and you want to create a pairing to make everyone happy, right? So there are a couple like definitions that are important for stable marriage. The first one is rogue pairs. So these are what you're trying to avoid. And a rogue pair is like a pairing in which they would be happier together than with their current partner. So there's a formal definition. If you have a pairing of M1 and W1 and M2 and W2, then a rogue pair would be M1 and W2 if M1 prefers W2 to W1 and W2 prefers M1 to M2. And one thing to help us with like creating stable pairings is the stable marriage algorithm, which we learn in class. So so the input to the stable marriage algorithm is pretty much a preference list. So each man will rank his preferences of females, and the females will rank their preferences of men. So you feed this into the stable marriage algorithm, and it outputs pairings that don't have rogue couples. So here's a stable marriage algorithm. So each morning, a man will propose to the most preferred woman on his list who hasn't already rejected him. Each afternoon, women collect all proposals and accept the man she likes the best. So she tells him maybe. And then on the evening, each rejected man crosses off the woman from his list, right? So the algorithm terminates if each woman has a man. So let's do a quick run through. So take a quick look at the ranking list here, and we'll use this to do a run through of the stable marriage algorithm. Okay. So on day one, like you saw here, Alex and Charles will both propose to Anita, and Bob will propose to Bridget, right? So that's what happens. And then after that happens, now Anita has a choice who to pick from Alex and Charles. So she prefers Alex. So Charles will now have to cross Anita off her list, right? And then the next day, Alex will propose to Anita, Bob will propose to Bridget, and Charles will propose to Bridget because he has to move down his list. And so he does so. And this day, it seems like Bridget also prefers Bob. So Charles will cross her off the list. And the next day, Alex will propose to Anita, Bob will propose to Bridget, and Charles will propose to Christine. So by show of hands, who thinks that the algorithm will terminate the next day? Yeah. And it does terminate the next day because they all propose to unique women. And now, so the termination condition was if every woman has a man. And so now every woman has a man and the algorithm will terminate. So yeah, there are 4 important lemmas about the stable marriage algorithm. And these are the 4. 1, stable marriage algorithm halts. 2, the improvement lemma. 3, the stable marriage algorithm terminates with a pairing. And 4, the pairing produced by the algorithm is always stable.
And so I'll quickly go through and give a quick proof of each of them. So lemma 1, the stable marriage algorithm halts. Well, the stable marriage algorithm, every day someone crosses someone off the list, right? Either that happens or the algorithm terminates. So there are at most n squared things on the list to cross out. So after at most n squared days, the algorithm has to terminate. Any questions on that? Okay. The improvement lemma is if a man M proposes to woman W on the kth day, then on every subsequent day, she has a man at least as good as M on a string, right? So woman W, after being proposed by man M, can never do worse than man M. And you can improve this by induction on the days. Yeah. The third lemma is the stable marriage algorithm terminates with a pairing. You can prove this by contradiction. So say M ends up without a pairing when there are n men. Well, he had to have proposed to all the n women, right? And they also have another man on a string. So then you know there must be at least n plus 1 men. And the last lemma is the pairing produced by the algorithm is always stable. And you can use a direct proof for this. So say M and W are paired, then there's no W star that M proposes, M likes W star more. So for any W star that M likes more than W star will not like M more than her partner because she will have to have rejected M. Yeah. So the last thing I want to say is that there's this concept of optimality. So the stable marriage algorithm is just one way to generate some pairings that are stable, but it's not the only way. So yeah. So let's do some practice problems, and there are 5 true and false questions. So for number 1, can I get a show of hands if you think it's true? And who thinks it's false? Okay. Yeah. So number 1 is true. In a stable marriage algorithm execution, which takes n days, there is a woman who does not receive a proposal on the n minus 1th day. And that's true because the termination condition... Sorry about that. I don't know what happened. Yeah. So, if every woman receives a proposal on the n minus 1th day, then the algorithm would have terminated on the n minus 1th day, right? So, that's the proof of that one. Take a quick look at the second question. So who thinks the second question is true? Who thinks it's false? Okay. The second question is true by the improvement lemma. Once someone is proposed to by a man M, then you know she has a man at least as good as M, right? Okay. So the third question. Who thinks the third question is true? Who thinks it's false? Who needs more time? Okay, I'll give it a little more time. So first of all, what will happen if every man gets his least preferred woman? You have to like go down the preference list, and everyone ends up at the last column, right? Yeah. And every day that someone gets rejected, there's also someone who doesn't get rejected, right? So let's go over 3. Who thinks that 3 is true? And who thinks that is false? Okay. Yeah, 3 is false because the algorithm will terminate as soon as one man has proposed to all the women, right? Because once one man does that, then every woman will have a man, right? And there's no way that all the men can like race down the list fast enough to all get their least preferred woman. Okay, so let's do question 4. Okay, who needs more time on question 4? Okay, raise your hand if you think question 4 is true. And if you think it's false. Okay, so question 4, 3, 4. Yeah, question 4 is true. So you can get an example for this. Like, if you just have the men rank their favorite women, and the women, like, have the opposite ranking pretty much, and then that will terminate on the first day, and each woman will like have her least preferred man. Let's do question 5. So who thinks question 5 is true? Oh, who needs more time? Sorry, okay. Okay, so by a show of hands, who thinks question 5 is true and false? Yeah. So question 5 is true, and it's by the improvement lemma. Okay, everyone good? Okay, so now we'll move on to graphs. So graphs are like a useful abstraction we learned. They're like a simple model to capture the essence of a complex situation, and they can be represented by a set of vertices and a set of edges. So some terminology for graphs: there's pass, walk, cycle, tour. A path is like going from one vertex to another. So the sequence of edges that go from like v1 to v2, v2 to v3, to vn. And a walk is pretty similar, but a path is simple, and a walk is not, which means like it can repeat vertices. And a cycle is a path that goes back to itself, and a tour is just a walk that goes back to itself. And we have directed and undirected graphs. So the only distinction is that in a directed graph, edges have directions, and undirected graphs, they don't. And then there's this concept of connected and disconnected. So every graph can be broken up into a bunch of connected components. So disconnected just means that, connected means that you can go from one vertex to everything else in that connected component. And then if it's disconnected, then you can't go. So let's do a practice problem. So try doing this problem with induction on the number of vertices and also on the number of edges. Okay, so let's go over this problem. I'll just go over induction on the number of edges. So to induct on the number of edges, we have our base case. If there's 0 edges, then the number of vertices with odd edges are 0, so that's even. Then we use our inductive hypothesis. So just assume that with n edges, then the number of vertices with odd degree is even. And then for our step, we consider graphs with n plus 1 edges, right? Then let's remove an edge from the graph. And then we know that the graph with that edge removed, it has an even number of vertices with odd edges, right? And then now we're going to add that edge back. So adding that edge back can do 3 things. That edge will only affect 2 vertices, right? So those 2 vertices could be odd, even, or even. If they're odd, then you'll lose 2 vertices with odd edges. So it'll be a -2 to the number of v-odds. If it's odd even, then it won't change the number of v-odds. And if it's even, it will add 2 to the number of v-odds. So then when you add that edge back, it's still even. Any questions on that? Okay. Okay, so now let's move on. There's Eulerian walks and Eulerian tours. Just something we learned, I guess. And another thing is special types of graphs. So we learned about like 3 big special types of graphs. There are complete graphs, which have the max edges possible, and that the line, triangle, and square thingy, they're examples of complete graphs. And we also learned about trees. So trees are like the opposite of complete graphs. They're like the minimal edges, number of edges to be connected. So let's do a quick question on trees. There's odd and even, then the odd will become even and the even will become odd, because you're going to add another one, right? And so there'll be 0 change in the... Oh, also, say the maximum number of leaves and prove that it's the maximum. So does anyone have an idea of what the maximum number of leaves is? n-1? Yeah, that's the maximum number of leaves. So now try to prove that that's the maximum number. Okay, so let's go over this question. The maximum number is n-1 leaves, and that happens if you have like a star graph thing. And we can prove this by contradiction. So we're going to say the max is n-1, and we can't have any more than n-1. So let's say by contradiction that we can. So we'll have n edges, n leaves, right? So that means that if we pick any vertex in the graph, it's a leaf. So if we pick x, we know x is a leaf, so it has one thing connected to it, so that's y. And then we know y is also a leaf, so it has one thing connected to it, it's x. And then it's no longer a tree, right? Because x and y are just their own little connected component. So that's the proof for that question. Question? But you can actually make a graph with like n-1 leaves. So you just like give an algorithm for creating a graph with n-1 leaves. You just like designate one as the root and then put all the other ones like around it to make a star. And then that will always give you a graph with n-1 leaves. So for every graph you can do that, you can get n-1 leaves, and for no graph you can go beyond that. So you can make n-1 and you can't make any more. So that's the max. Okay. And the last kind of like cool graph we learned about is like a hypercube. And for this, there are two ways to make a hypercube. One is by building up hypercubes from smaller hypercubes. And the second one is like with the bit string thing. So you can start with like 2 to the n vertices, and each of them represent like one bit string. And then you connect them with edges if they're different in 1 bit. So let's do a quick question on hypercubes. So a hint for this one is to consider the bit string way of making a hypercube. Yeah, the bit string thing is you start with 2 to the n vertices, right? So let's say like I have 3 bit strings, like 3 places. Then I can create like a hypercube with 8 vertices, right? One will be for 0, 0, 0, one will be for 0, 1, 0, one will be for 1, 1, 1. And then we connect them only if they're different in one like digit. So 0, 0, 0 will be connected to like 1, 0, 0, 0, 1, 0, 1, 0, and 0, 0, 1, right? It's connected to 3 things. Does that make sense? So for this question, to be a distance of 6 away, it means that you have to be different in 6 positions, right? So does anyone have an idea of what the answer to this might be? Yeah. Yes, n choose 6, because there are six positions in which it's different, and now you just choose the 6 positions. So the answer to this is n choose 6. Okay, and that's all I have.
Maybe it's this one. Yeah. Or they're different. Yeah, so this will be VGA.
Oh, but this is HDMI, right? Maybe we can try this.
Oh, just using this? Yeah, maybe.
Okay, hello. I'm going to cover modular arithmetic, bijections, and RSA. Okay, so just some simple reminders. There are 2 properties of addition, subtraction, and multiplication with modular arithmetic. So as an example, if I wanted to calculate 8 plus 5 mod 5, I can first apply mod 5 to 8 and 5 individually before summing them up, or I could compute 13 mod 5 and then just figure it out from there. Okay, and similarly for the multiplication case, I can mod individual components of the product before taking their product, or I can do it afterwards, and you would get the same result. Okay, so the complicated case is where you come across division. So technically there's no strict division within modular arithmetic. What you have to do is compute the multiplicative inverse. I'm pretty sure you're familiar with it. So just keep in mind this theorem. The multiplication inverse exists if and only if the GCD of n and x is 1. Moreover, if it exists, then it is unique. Okay, so how do we calculate the GCD? This is Euclid's algorithm. It's based on the theorem that the GCD of xy is the same thing as the GCD of y x mod y. Okay, assuming that x is greater or equal to y greater or equal to 0 and x is greater than 0. Okay, so this is the tabular form of finding the GCD of two numbers using Euclid's. So let's say I wanted to find the GCD of 13 and 17. So we want x to be the larger of the two numbers, so we can just switch the two and make it 17, 13. And then we can go down this table, move whatever was y, whatever value y was in the row above to the x value to the row below, and then calculate x mod y for the y value below. Okay? So the final answer is 1. This means that 13 mod 17 has a unique multiplicative inverse, and so does 17 mod 13, which is the same as 4 mod 13. Okay. So this is the extended Euclid's algorithm. It's just slightly modified to return D, A, and B. So you throw in x and y as input as before, but now you have D, A, and B back. And they're related by D equals AX plus BY. Questions? Okay, so D is the GCD of x and y, and you can figure out exactly how they're related because you get A and B at the end. So this is helpful for finding the multiplicative inverse, which we will see an example of. Okay. All right, so here's the example. Let's say I wanted to find 13 inverse mod 17. Again, you have the same two columns on the left, but I'm going to add 3 more columns on the right, D, A, and B. I'm going to first traverse down through the first 2 columns. This is just the same as before. I reach the base case, 1, 0. And then I return 1, 1, 0. So remember, x 1, 0 is the base case. This is just applying extended Euclid's. So I go up, and at the very top, I reach D equals 1, A equals -3, and B equals 4. So what does that mean? That means that 1 equals -3 times 17 plus 4 times 13. Okay? And then to get back to the original question, if I wanted to find mod 17, I just apply mod 17 to both sides, and here you go. We find that 4 times 13 is 1 mod 17. So therefore, the inverse of 13 mod 17 is just 4. Are there any questions about this example? Okay, cool. And the specifics are over here. Okay, so I know bijections was previously covered really quickly. But I included like a few pictures, so hopefully that will help. So remember, the definition of a bijective function has both 2 properties. They have to be onto and one-to-one. So here is a picture. So let f be a function that maps each element of A to an element of B. So it's onto if each element of B has some pre-image on the left. So what does that mean? That means every element in B is pointed to by some arrow. Okay, and then it's one-to-one, meaning that if 2 arrows point to the same element on the right, then both arrows must originate from the same element on the left. Okay, so remember this lemma. A function f mapping from the set A to itself is a bijection if and only if there is an inverse function g such that g of f of x is x and f of g of y is y for all xy within the set A. Okay? So you can sort of see it's kind of like before, but now we have set A on the left and set A on the right. And again, the function f maps every element from the left set to the right set. And because we know that the inverse function g exists, g of f of x equals x shows that it's 1-to-1, and f of g of y equals y shows that it's on 2. Okay. All right. Okay. So FLT for any prime p and any a that is not 0, so it's 1 through p minus 1, we have this property where a to the p minus 1 is 1 mod p. Okay. Any questions so far on what I covered? Okay. RSA. So just as a reminder, this is basically how the algorithm or the scheme goes. Anyone can send a message to Bob where no one except Bob could decode the message. So E of x is the encryption function, x to the e mod n. And then to decrypt, you just take whatever the encrypted message is and raise it to the dth power, mod n. Okay, so remember, Bob first picks two large primes p and q, and he calculates n by multiplying them together. He also picks an e that's relatively prime to p minus 1 times q, p minus 1 times q minus 1. He will compute the secret key or the private key d, which is the inverse of e mod p minus 1 q minus 1. The information that's public is n and e, and then d, p, and q should be kept private to Bob. So someone wants to send Bob a message, so they can just encrypt their message with by raising the message to the eth power mod n. When Bob receives the message, he can decrypt it by applying the decryption function. And then, so just as a property, an eavesdropper without the private key d cannot figure out x because brute forcing is inefficient. Usually p and q are really large numbers, and it's just not possible to figure it out with any good chance. It's hard to factor n to p and to q, and it's hard to compute p minus 1, q minus 1 directly. So these are all inefficient ways. That's why RSA is considered good. Okay, so before we move on to practice problems, are there any questions about what I covered? Okay, cool. So true or false? Assume a, b, and c are integers and c is greater than 0. If a has no multiplicative inverse mod c, then ax equals b mod c has no solution. True or false? And explain your answer. So let's take about 1 minute. Okay, does anyone need extra time? Raise your hand. Okay, 20 more seconds. Okay, so how many people think this is true? Please raise your hand. How many people think it's false? Raise your hand. Yes, the answer is false, and here's a counterexample. So you could have a situation where x has multiple solutions. Okay? Any questions? Okay, cool. So I guess since we're running out of time, why don't we just try the first one? Let's spend 1 minute on it, or at least figure out how you would approach this problem. Okay, I think I'm going to go over the first one. Does anyone desperately need another 30 seconds? Nope. Okay. So here we take a look at the exponent, which is 570 to the 571. And we can split that up into 570 times 570 to the 570th power. So note that this is just 570 multiplied by another constant, which we can call c. So hence, we can rewrite this huge number in terms of 569 to this 570. All of that raised to the power of c. So here, the hint says 571 is prime. We can apply FLT. And so whatever's in the parentheses reduces to 1, and 1 to the cth power is always 1. Okay. And I know we didn't have time to do the second part, but similarly, 31 is a prime number, so 7 to the 30th power is 1. And by rearranging the exponents, we can figure out that this value reduces to 14 mod 31. Okay. Are there any questions? Yeah.
I have no idea what you just did to get there.
Okay. So, sorry. FLT is, so if this mod is a prime number, so in this case it's 31, that means any power that's not 0 raised to, so any number that's not 0 raised to the power of p minus 1, which in this case is 30, will always reduce to 1 mod p. Right? A to the p minus 1 is 1 mod p. Oh, okay, yeah. So then all you have to do is see how many multiples of 30 there are in the number 2014. So you can rewrite 2014 in terms of 30 times 67 plus 4. So 30 times 67 plus 4, in that case, you can rearrange, split out the exponents to make it look like this, right? So 30 times 67, whatever's in here reduces to 1, right? 1 raised to the power of 67 is still 1. All that's left is 7 to the 4th power, which is a lot easier to calculate. Okay. Does that make sense? Okay. Any other questions? Okay. Cool. So I guess we might just skip this problem because, or does anyone want to do this problem? It's just basically arithmetic calculating the private key and the encrypted message. Okay, well, okay, I'll post these slides online so you'll see. And this is an interesting practice problem, but it's also kind of challenging. So it's a very long solution. So because we're running out of time, I think we'll skip this for now, but feel free to take a look online on your own time. Okay, so, but in general, any other questions on what I covered? Okay, cool. Yeah, sorry.
If you find E and D for RSA mod P minus 1 mod P minus 1 times P minus 1, how do they come out to be the same thing mod n, which is PQ? Does that come out to be 1 mod PQ?
Oh, so FLT is different from the encryption function of RSA. So FLT is just this property over here. It's usually we kind of decouple it from this finding the private key. It's usually different. So the reason why we talked about FLT in the notes was to prove that this was a bijection. Yeah.
I don't understand if you're computing E and D
Uh-huh.
mod P minus 1 times Q minus 1.
Okay.
Why is X times E D mod n just X?
Oh, it's not X. It's usually some other number. What?
Why does decrypting it work?
Why does decrypting work? Okay, so there's a very lengthy proof in the notes. I can like come talk to you after. We can go over it together. Okay. But any other questions? Cool. All right. Thank you.
How does this? It's like too many things.
to turn it on?
I think maybe the other one. Or do you not have HDMI?
Don't think so. I do not. Sure. Yeah.
I don't know if I have it.
I guess I added it today.
I have not done this in a while.
Yeah, polynomial solution. I think that should be yes. Great, thank you.
Okay. So just one more section. If you have to leave, you can go. It's just polynomials, secret sharing, and error correcting code. Okay. So pretty much for polynomials, there's like two important properties. The first property is pretty straightforward. It's just that a non-zero polynomial of degree d has at most d roots. And then for property 2, given d plus 1 pairs, with all distinct x values, there's a unique polynomial p of x of degree at most d that falls on these points. Okay, so degree d polynomials are generally defined by d plus 1 points. Okay. And then we have polynomial interpolation, and there's a couple ways to do this. More than a couple ways, but two of them are right here. So system equations, that's pretty straightforward. You just if you know what the degree of your polynomial will be, you just set up a system of equations and you solve for the unknowns, which are just the constants in front of the variables. And then we have Lagrange interpolation, which is setting up delta functions. And this is pretty much what you do. Just a quick review is you basically just find the delta I such that delta I of xi equals yi. Or actually, I think it should equal 1. Yeah, so that's a typo. So it should equal 1 for all I. And then you find your f of x, which is just the summation of all of those times their corresponding y values. Okay. Any questions so far? Okay. And then there's finite fields. And basically what we're doing here is we're restricting the domain and the range. And we're only dealing with a finite number of them. Okay, so when we do GFP, then we're saying that the domain and the range are all going to be restricted to be in the discrete integers between 0 and p. Okay? And then pretty much the properties 1 and 2 still hold because we still have addition, subtraction, division, and multiplication. Okay. And next is secret sharing. And this is pretty straightforward too. So for secret sharing, pretty much all you do is you just define the polynomial with your secret in whatever position you want it to be in. And then you just hand out however many. Well, then you make sure that the polynomial is of degree k minus 1, where k is the minimum number of people to figure out the secret. And then you just hand out the points. Okay, and then if those k people gather together, then they can figure out what the polynomial is, and they can recover exactly what your secret is. Okay, so pretty straightforward. I hope. And so we have like a simple interpolation problem, but this is really just like busy work, so I think we can skip it. There's the solution. So you can look that up later on your own time, but it shouldn't be too hard. And you can see like basically what you're doing here is you're just normalizing each of the delta functions based on the value that it's currently at. Okay, so that you guarantee that it'll be 1 at that point. So pretty straightforward. And then for secret sharing, here's like a kind of cool little problem. Yeah, let's work on this. So just take a few minutes to try to figure this one out. And if you have any questions, as always, just raise your hand. Ooh, not bad. Okay, so who needs more time? Just raise your hand. Looks like no one. Okay. So pretty much you just do a 2-level scheme of secret sharing. And I may have gotten the degree of the polynomials wrong. But pretty much what you do is you just guarantee that only... so you like define your secret, right? And then you define a polynomial that... a degree 1 polynomial so that you can pass out secrets for each group. Okay? And then within each group, then you define a new polynomial such that it requires 4 people to recover the point on the original polynomial. Okay? So then with those two combined, then you define your secret, essentially. Okay. Any questions on that so far? Okay. So then error correcting codes, we have 2 types of errors. The first are erasure errors, which are just that packets were lost or erased. And then we have general errors, which are just that packets were corrupted. Okay. And then dealing with erasure errors is pretty straightforward. You just make sure you send k extra packets, and then if those packets are dropped, you still have enough points to redefine your polynomial and recover your message, regardless of what packets were dropped. Okay? And then general errors is like you have to send n plus 2k packets, and then the receiver will just run Berlekamp-Welch, which we'll go over right now. And so Berlekamp-Welch, what happens is it's a little complicated, but if you work through everything, like each step on its own is pretty straightforward. So we have like so many packets that we've sent, and we want to find the original polynomial p of x, where p of x was defined by n points, okay? So we know that there are a bunch of corrupt packets, so we can define some e of x that takes on the value 0 for all of the corrupted points, okay? And then we define q of x equal to p of x times e of x. And we know that our property, so that's what we define. And then since we know that p of x is a degree n minus 1 polynomial, and e of x is degree k, then we know that q of x is degree n minus 1 plus k. Okay, because we just multiply the two together. And e of x is degree, it's degree k, and it has k unknowns, like you can see right here, because the first value is always known to be 1, because of how we defined it, right? Because we just defined it to be multiplying out x minus e1 times all the way up to x minus ek. Okay. And then we just set up the equations using qi equals ri times e of I for all of our points. Okay? And that means that we have n plus 2k unknowns and n plus 2k equations. And then we're pretty much guaranteed a solution. Okay? And then you just find p of x by dividing e of x out of q of x. Okay, and then we have like a problem for applying Billikamp-Welch. Do you guys want to do this? Like, it might not be super useful. I think something more useful is just to go home and like end this review session. So yeah, good luck on your final and everything.